Welcome to the course Business Analytics and Data Mining Modeling using R. So let's continue our discussion on classification and regression trees. So in the previous lecture we were talking about we were discussing the pruning, the second step of classification and regression tree models. So we talked about the pruning and different approaches to avoid overfitting in the full grown tree model. So we talked about pruning approach and two ways: validation partition, using validation partition to find out the exact point where we can stop, where we can prune back the tree to that level, or using cost complexity or complexity parameter values to control the tree length. Now the next related concept is a minimum error tree. So as we talked about in one approach, that the validation partition can be used to find out the point at which from where the error starts to increase. So the tree with minimum classification error on validation partition, that is called the minimum error tree. So the point where we achieve the minimum classification error. So first we build the tree model, and then we look at first we build the tree model, then we look at different candidate models. So the tree, as we talked about, full grown tree, and if it is being pruned back to certain levels. So for different levels of different pruned models, which could be which are going to be the candidate tree models for different for all those models, we can look at the misclassification error, where the misclassification error is minimum, and that particular tree, that particular pruned tree is going to be the minimum error tree. So let's move forward. Another related concept is best pruned tree. So this is the tree that ideally we would like to find out, we would like to determine, and then use it for our on our new data and for deployment as well. So what is best pruned tree? So best pruned tree can be determined using by adjusting for sampling error or minimum error tree. So the minimum error tree, there could be due to changes, due to samples. There could be that minimum error tree can move to some extent because of the sampling error. So how do we certain how do we find out the best pruned tree? So if we are able to adjust for sampling error, if we are able to identify a range right for the minimum error tree, that this is going to be the best pruned tree is going to be within that range of a minimum error tree. So that range would be actually the adjustment for sampling error. So typically how that is done, so smallest tree in the pruning sequence, right? So we need to find out the pruning sequence. So smallest tree in the pruning sequence which lies within one standard error of minimum error tree. So we need to find out the minimum error tree, and in the pruning sequence, then within the one standard error of the error rate, we have to check the tree which is going to be there. So the smallest tree in that sequence is going to be the best pruned tree. So typically if we have the pruning sequence, and if we have because it's a sequence, so it is going to be sorted. So therefore if let's say minimum error is let's say 0.1 and the standard is 0.01. So within the 0.11 range, we have to see the tree which is having a smaller number of nodes, right? So that is going to be the best tree. So let's try and understand these concepts through an exercise in R to get more clarity. Let's open R Studio. So let's start our pruning process. So when we have already done the modeling in the previous lecture, where we had built the model, full grown tree model using the promotional offer data set, right? So you can already see this was the model that we had. that we had built. So you can see the root node and other nodes of the tree. So this is the full grown tree. You can see, as we talked about, it's quite messy, too many new nodes are there and it's completely overfitting the data. So now we would like to prune it to some level where it is not overfitting the data or where it is not fitting to the noise. So let's start our pruning process. So let's look at the number of decision nodes, number of total nodes that are there in full grown this particular tree. So you can see 101 total nodes are there, total number of nodes are there in full grown tree. Let's look at the number of decision nodes that are there. So you can see 50 decision nodes are there, and let's look at the number of terminal nodes or leaf nodes, so 51. So as we talked about in the previous lecture as well, that because we have been building binary trees, so binary trees have the property that the number of leaf nodes or terminal nodes are always going to be one more than the number of decision nodes. So that same thing you can see here, the number of decision nodes are 50 and the number of leaf nodes or terminal nodes are 51, one more, and the total being the sum of these two numbers 101. Now let's look at the node numbers. So as we talked about the R part object in the previous lectures, and we talked about one particular attribute frame. So this particular attribute contains the row names, which are nothing but the unique node numbers that are being assigned. So these particular node node names are I think in the factor. These are, let's look at the class. So these are stored as a factor variable, I guess, character variable. So this has to be coerced into an integer because these are actually nothing but the node numbers. Let's look at the first 6 values of this particular attribute row names. You can see 1, 2, 4, 8, 6, 7, 16, 17. Let's look at the tree model. So had it been numbered, this would be row number 1, and this would be node number 2, and this would be node number 4, and then 8. So in this fashion, 1, 2, 4, in this fashion you can see the row names have been recorded here, right? And this particular code will give us all the unique node numbers that are there in the full grown tree. So let's execute this. So we'll have toss1. So if you are interested in looking at the unique node numbers, so you can see here. So we had 101 nodes, as we saw, total number of nodes were 101. So there are 101 elements in this particular vector, integer vector, and you can see the unique node numbers, right? 1, 2, 4, 8, 16, and you would see all the numbers are not covered, only the node numbers which are present, unique node numbers which are present, the part of the full grown tree, only they are recorded here in toss1. So now we would like to sort this particular integer. Reason being, we would like to identify the nodes which we would like to get rid of, because the idea is to remove the branches, right, which are not decreasing the error further, right. So let's sort these values. So once we sort, we will get toss2, this variable. You can see now the node numbers have been sorted, 1, 2, 3, 4, and up to 915, the last node number. Though we have just 101 nodes, the node numbers are unique, so therefore they take their range is going to be much higher. So 1 to 915 node numbers are present in the full grown tree. Now once we have done this, we can start counter for nodes to be snipped off. As we talked about, we would like to prune the tree back to a level where the error doesn't increase further. So first we will initialize the counter for nodes to be snipped off. So I1 is our counter. Now this another variable that we are initializing here is mod1 split v, and then we have mod1s train v, training vector, validation vector. So in these vectors we are essentially storing the models. model objects, R part model objects. Then we have error train vector and error valid v. So there we are storing the error rate, right, the overall error, the misclassification error for different level of different level of prunings, right. So as we keep on removing branches, so we'll get a subtree. For each of those subtrees we would like to record the error rates, so that we are able to compare later on from those error rates we are able to identify the point from where the error rates are going to increase. A similar kind of exercise we had done in Canon to find out the optimized value of k. So let's do the same thing here. So let's initialize some of these variables. Now we would see we are starting a for loop, and in this again you would see the x, that for loop counter will take values from this particular variable mod1 frame var. So you would see in the R part object you can go and look at the elf section, and you would see in the frame attribute it also records the variables which have been used for the splitting. So the split variables are recorded in this. So the counter will run for all the split variables, right. Now let's look at the next line. So this is if condition here. So you can see for this particular variable, if it's not leaf, and if the length of toss2, right. So the toss2, the series of nodes which from which we would like to create these different pruned models, right. We talked about different pruned models depending on the labels, depending on how we keep on removing the branches, and we will get different subtree models, different pruned models. So so this is the counter for the same. So I was the counter, so it will, this is the maximum value for it. Toss2 we have already computed, right. Then for every time we have to compute the actual nodes that we would like to snip off. The function for snipping we are already familiar, as we have used it in the previous lectures, snip.rpart. So there we need to pass on in the second argument is about the unique node numbers which we would like to get rid of, right. So this toss3 variable is essentially to record the same. So you would see that for counter, depending on the counter value, the next node number I plus 1 up to the last node number we would like to get rid of. So we will start from this smallest tree to the full grown tree. So in that fashion we are trying to create different pruned models, right, smallest tree to the full grown tree. So toss3 would actually capture this. Then you would see the next line is mod1 split. So there we are using snip.rpart, and so the toss3 that we have already computed, so those node numbers are going to be used, and we will get a subtree model. Now once that is done, so that model is going to be recorded in this vector, because we are going to create many more subtree models for this, and later on we will compare the error rates. Now once this model has been built, we are also scoring the training and validation partition. You can see here this training and validation partition we are trying to score off, and then also you would see later on here you would see that we are also recording the overall error for these two partition, training and partition. So we score them, and then we compute the overall error for training and validation partition for all of these pruned models. Now after that you would see that the I counter is back, and then the next subtree is going to be computed, and then performance is going to be recorded. So let's execute this particular loop. So it will take a bit time. Yes, computed. So now we have the list. Now we are going to create a table for where we have the that number of split and then the error for the training partition and the validation partition. So let's look at this particular table. So this is based on the computation that we have just done. So let's look at this. So you can see decision number of decision nodes 1, and error training and error validation is there. If number of decision nodes are 2, then what was the error, and what was the error in the validation partition, what was the error in the training partition, so that we can see. You can see the error in training partition is decreasing, and the same is true for validation partition also. The error is decreasing, but the rate of decrease in the training partition is much more, and you would see that these errors keep on decreasing, and you would see that this in the validation partition we are interested in this one 0.16. so it has decreased up to this point, number of decision nodes 9, and it has decreased up to 0.016, and for one more node also the same error rate is there, and then it just starts to increase. You can see 0.018. so now this is the point, probably node 9 and 10. so these are the two candidates which are recording the minimum error in the validation partition. You can see this 9 decision nodes, model with 9 decision node and model with 10 decision nodes. so these are recording the minimum error, right, and after that the error starts to increase. However, if we look at the error in the training partition, it it still keeps on decreasing, right, because we start to overfit the data now, or we start fitting to the noise. So therefore you would see that in the training partition the error is still keeps on decreasing. However, in the validation partition the error starts to increase, right, and as we go down to the full grown tree, we go down to the full grown tree labels. So you would see that the error in the training partition has reached to 0, and for the validation partition it is much more, right, much more than the lowest minimum error that we saw. So at this point I would also like to tell you that this table that we have just computed, it is actually based on the sequencing of the nodes, right. The node numbers you can see so you can see node number sequence, that is node number 1, 2, 3 in that fashion, because we had sorted the node numbers, right. We actually saw that the sequence that we are using to snip off the nodes, that is the sorted sequence 1, 2, 4, 8, 16 in this fashion. This was toss 1, this is the toss 2. so the this is sorted sequence of node numbers. So the snipping or the branches that we are removing in this particular example is actually in that sorted sequence. However, what is expected is that we should be snipping off the branches based on the pruned sequence, right, order in which the complexity, for example, if it is based on the complexity parameter values, right. So for once the first split has been created, so we need to understand whether the second the split on node number 2 is going to be the optimum, or next split on node number 3 is going to be optimum, right. Let's understand here. So for a root node we need to understand that once a particular split has been performed, predictor 1 value 1 at root node, right, and then we reach here. So we have two options now, where should the next split be performed, here or here. We can always find an optimum split for the node number 2, and we can also find an optimum split for node number 3. So which should be the next split? So that is going to be determined by the impurity reduction, right. So P2 V2 here and P3 V3 here. So therefore if the impurity reduction on this particular half for the right subtree is more, then the split number 1 is this, split number 2 is this, and then again further we will have to compare for the third split between these nodes, which one is giving further reduction. So that is going to be the that is called the pruned sequence. So rather a better term is the nested sequence. So the most important split, then the second most important split, and in that sequence. So the sequence of splits in terms of based on importance, right? Importance means impurity reduction. So that is the sequence that we should be using actually to remove the branches. But what we are doing in our exercises, we are just going in the sorted order fashion. So first node number 1, then node number 2, then node number 3, node number 5. So we are in our exercise, what we are doing is we are following this sorted order, which is not actually same as the sequence of splits based on importance. So this exercise you can do. However, what we are trying to do here is we are just following the node order of the node numbers, and that is not actually the sequence, the nested sequence or the sequence based on the importance, right? So the least important split should be removed first, right? And that is how we need to prune the tree. However, we are following the order based on the node numbers. So even with that, we can understand the process, right? How the tree can be pruned back to some levels using the using different function available in R. So based on that, we can move further. So we can also look at the tree after last snipping that we did. However, we would like to move further, and we would like to plot the error rates that we had just created. So let's look at this, the plot. So these are this is the plot for the error rate versus number of splits that we have just computed. However, these computations are based on the node numbers ordering and not on the based on the importance, right? So that I have just discussed. So even from this computation, we can see that the error for this is the validation, this is the training partition, you can see. So this goes like this. So the error keeps on decreasing, right? So error keeps on decreasing here for the training partition. If we look at the validation partition, the error decreases, but at some point it starts to increase, right? So at some point it starts to increase. If we go back to the table that we had generated, right, in this table, if we look at the number where it was minimum, we can look at the number of decision node 10 and number of decision node 9. So they had these lowest error values out of all these points. So node number 10 and 9 are going to be here, somewhere here, and you can see the validation error value is also minimum somewhere at this point. So probably this is the point which is going to be the point with respect to minimum error tree, and within one standard deviation of this point we can actually determine the best prune tree. So after this we can see clearly the remaining partition. So after 9th and 10th splits, all the remaining splits, about 50 splits, all of them are actually fitting to the noise or overfitting to the data. So with this let's move forward. So what we try to do now is we will try to identify the minimum error tree and then best prune tree as well. So we can simply use the min function to find the value of the error of the minimum error tree. So this is the error 0.016, which we find out looking at the table as well. Now we are interested in finding out the number of nodes that are going to be in this particular tree, so that we can also find out. You can look at the code. Number of splits, and we are trying to identify the error value where it is minimum, and that number of nodes will get as this. So you can see 9. So we had two values, rows 9 and 10, both having the same, but the minimum first one of them has been selected. So minimum of that has been selected because this min function on n split has been applied. So out of 9th and 10th, 9th is a small number, so that has been recorded here. So the minimum error tree will have actually 9 decision nodes, So let's look at the standard error that we talked about. So we need to find out the best prune tree is going to be one standard error within this one standard error of the minimum error tree. So this is how we can compute the standard error. So variance of error validation vector, that error rate vector that we had, and divided by the length of the same vector, and taking the square root of the same will give us the standard error. So this is the error. Now to find out the best prune tree, let's compute another error. So as we talked about, because this is a kind of a sequence, right? So we have to go to the left side. So therefore the trees that we have to look at the in this is going to be within this range, the minimum error plus this standard deviation, and then with this standard deviation we can compute this value. So our best prune tree will be the smallest tree having error value less than this particular value, MET1 STD. So this value, so our best prune tree is going to have the error on validation partition less than this. So how do we find out that particular tree? So this is slightly still the table we have already computed. So from the table also we can find out. So let's do this exercise using table first. So 0.0180 is the number that we would like to compare with. So we have to go to the left side. So the smaller number of nodes. So we can see we go to the left side. The first number, the decision number, the 8th row, where a number of decision nodes are 8. So this is the tree that is going to be selected as best prune tree from looking at this number, right? Because this particular value 0.018 is smaller than the value that we are looking for, one standard deviation. So it is within the one standard deviation of minimum error tree. So the best prune tree would actually have 8 decision nodes, right? So the same thing we can also compute using this particular code. You can see we are looking at the range. So which of the rows are having error less than the minimum value, and then greater than the minimum value but less than the that particular range that we have just computed using MET1 STD, and also the number of nodes there should be less than the minimum error tree. And so there could be more rows here. So we would like to identify the first one because that will have the smaller number of nodes. So once we compute this, you can see we got 8. Had this table been a bit a bit longer, still we would get the right answer. If there had been 2-3 candidates, we would get the right answer. Now once we know that 8 decision nodes are required, so we can again follow the same procedure that we did earlier. The toss variable that we require to snip the tree, we can use, we can remove all the remaining nodes. So again here also we are following that node number sequence. So we are keeping the nodes from 1 to 8, and from 9 to other nodes we would like to snip off. However, this is not the suggested way of doing. We should actually follow the we should actually remove the splits which are least important, and that sequence has to be followed rather than the sorted sequence as we are doing in this example. So let's do this for an exercise. So we compute this toss3, then we call the snip.rport function and pass this argument, and we'll get the subtree, and then we can print this subtree here. You would see. So this is the subtree that we have generated through our exercise. However, this is not the desired result that we wanted. Just for an exercise we have done this. We have used the node numbers, you can see. So the way we have that approach that we have taken, we are always going to get this kind of tree which is going to be fairly balanced, right? So because we are not following the that important splits criteria. So you would see this tree is always going to look like this. Now this is, so this tree is much smaller than the full grown tree that we had earlier, right. So now it has been pruned to this level, and we can also see the important variables and value combinations and other things. Now we can apply, once this particular tree has been built, we can apply this particular tree on our training and other partitions to look at the performance of this particular model. So again, predicate function we can use, and let's score the training partition, look at the accuracy number 97.4, right. Then let's test it on validation partition. Now you would see that validation partition is also part of the modeling exercise. The performance is slightly better than the training partition. You can see in the full grown tree the performance was continuously decreasing, but here we would be surprised, we should not be surprised that the model, because now it is pruned model, so it is giving a much better performance in comparison to the training partition. However, the performance, what we expect is performance to remain a bit stable. However, still even with the prune tree or best prune tree, we expect that the performance on new data test partition and other partition should actually, we expect that to go down. However, it should be stable for any new observation that we would like to predict. So if we look at the test partition and the performance on test partition, that is 98, that is even better. So you can see the best prune tree is performing quite good on new data. However, again I would like to remind, we have not followed the actual process to arrive at this best prune tree. So this that actual process we will do in a later lecture. Let's a few other important concepts that I would like to cover here is the complexity parameter. So complexity parameter, so the particular function R part that we use. So I already discussed this, that by default it reserves some of the observations for cross validation purpose, and based on those observations, the model, the remaining observations are used to build the model, and these observations, reserved observations, are then used to test those models, tree models, to look at the same process what we did, to look at the performance, performance on those observations, and the number of and the particular number of splits where the performance is on the lower side. That could be one of the candidate to get the prune tree. So we'll stop here and we'll continue our exercise in the next section, where we'll see the inbuilt complexity parameter that is there in R part, that can be, how that can be used to achieve the prune tree. Thank you.